so much. And good morning, everybody, or selamat malam, depending on where you are in this world. Thank you so much for being here today. I almost started crying before we even started, so that was not good. And getting here has not been easy, if I have to be honest with you, especially this past year doing the research amidst everything that's going on in this world, including the pandemic, was quite challenging. But remembering that this fishery that I'm researching positions Indonesia as the second largest global snapper exporter, it means that with or without a pandemic going on, the research must go on. So here is my dissertation. It's titled Characteristics and Potential Management of the Indonesian Deep Slope Fishery. And first, to orient ourselves, this fishery is based out of Indonesia, which is in this orange map right here, born and raised in Indonesia. But right now, I'm here in Providence, Rhode Island in the United States. And you might realize, wow, like Indonesia is actually quite large. It's about the same width as the United States. And you're absolutely correct. What's different is that Indonesia's coastline is more than 3 times longer than the coastline of the United States. That's because it's separated amongst more than 17,000 different islands. So when we start to think about fisheries management, it starts to become very apparent how complex, how difficult it is just for data collection, monitoring, and enforcement. So focusing a little bit more on what this fishery is about, let's start with the deep slope part of this fishery. And that's just the habitat where the fishing occurs, which is either continental shelves, slopes, or seamounts. And the main fishing gear in this fishery is either long lines or drop lines. And the vessel sizes really ranges from 1 gross ton or GT to 150 GT. And the fishing occur at deeper areas, well, deep slope, between 50 to 500 meters. And long lines tend to fish less deep and drop lines tend to fish in deeper areas, but that is not always the case. And the demersal part, it just means that the target species in this fishery is bottom associated. So in this case, this fishery targets more than 100 species of snappers and groupers. So what does 100 species of snappers and groupers look like? It looks a little like this, and it looks a little like this too. And that's me. We're in the middle of a fish market in East Java. So we're starting to see that this fishery is quite complex. It's also data poor and it's not managed very well. But there are different ways to deal with that. So first, we always start with the fishery data, and then we take the data and do assessments using different fishery indicators. And depending on your assessment results, you can get a good result for your fishery, or you can not be doing so well. And depending on your assessment results, you take different management actions. And in this case, if the fishery is already doing pretty well, then the management action that you need to take is just to maintain it at that level. And if the fishery is not doing so well, there's different ways or different actions that you can take. Just for example, you can control fishing effort, like by limiting licenses or gear restrictions, but those are just examples. And there are different fishery indicators that we can use to do fishery assessments. So first, we have a length-based fishery indicator where you use life history parameters. And this is based on the assumption that the fish length represents the fish age. So there are 4 different life history parameters. First, we have the length at maturity. Then we have the optimum fishing length, which is the length at which the biomass of the fish is the greatest. Then we have the asymptotic length, or how big the fish grows. And then we have the maximum length. That's that one largest fish ever. And what's pretty cool about these life history parameters is that there's known ratios between them. So once you know one of them, you can start to calculate the rest. And so in a fishery, ideally, you want to be catching 0% immature, because you want to let the immature at least grow and spawn once before you capture it. And then you also want 100% of the catches to be larger than the optimum fishing length, and about 20 to 30% at around that asymptotic length. The next fishery indicator that is very frequently used in fishery assessments is the catch per unit effort, or CPUE. And this is based on the assumption that the catch is proportional to the abundance. To illustrate that, imagine there's 2 different fishing grounds, one with a higher fish abundance than the other. If we're fishing each fishing ground using the same fishing effort, then you would expect to be catching, well, more from the higher abundance fishing grounds. The next fishery indicator is spawning potential ratio, or SPR, which is the ratio between the spawning stock biomass, or SSB, in an exploited fishery and in a pristine fishery. And here the spawning stock biomass, or SSB, just means the mature fish in the population. So higher SPR means that it's better, because as the SPR declines, that means there's less and less mature fish in the population. And then if it keeps on declining, eventually there's not going to be enough mature fish to spawn and replenish that fish population. So typically we use SPR equal to 40% as the target reference point. And this just means that the fishery is doing pretty well and we want to maintain it at least at 40%. And we use 25% as the limit reference point, typically. And this just means that, all right, fishery is not doing really well, and now we need to change it and bring it up so the 25% becomes at least 40%. And the last fishery indicator is the trade limit, which is different price premiums depending on the fish size. So if there's a price premium for small immature fish, then the fishery has a higher risk to overfishing. And conversely, if there's a price premium for the larger fish, then the fishery has a lower risk towards overfishing. So we know that this fishery is a data poor fishery. We know that it's a multi-species, different gear types, different vessel sizes, from the smallest canoes to the largest vessel sizes, and it's spread across many different islands. So in this research for my dissertation, I aim to characterize the characteristics of the fishery and then hopefully use that to come up with different management strategies. So in this dissertation, it's split up throughout different chapters. So for the first two chapters, it's all focused on the data collection method, about the development of the data collection method and testing the data collection method itself. And this was done in collaboration with Yayasan Konservasi Alam Nusantara, which is the Indonesian TNC, which I'll just refer as TNC from now on. And for subsequent chapters, I'll try to characterize the fishery and then use the fishery indicators that we just discussed to assess the sustainability of the fishery. And finally, we'll wrap things up with trying to figure out how we can improve the sustainability. So let's start with the data collection method. So prior to becoming a graduate student here at the University of Rhode Island, like Austin mentioned earlier, I was working with the TNC in Indonesia, and that's where we developed this coders data recording system, or crew operated data recording system. And in this data recording system, first we're trying to get catch data. And to do that, we use cameras and a measuring board. So we equip different captains and the vessels with a measuring board and cameras, and we ask them to place each fish of their total catch on the measuring board and take photos of it. And we also equip them with GPS trackers that automatically records the coordinates 1 ping per hour. And from these two different data streams, we get the species and length data, and we also get fishing ground information. Since 2015, coders have been deployed all throughout the Indonesian archipelago. And until August 2020, we have collaborated with more than 600 fishers. That amounts to 3.5 million pictures of fish, and that came from about 16,000 fishing trips. So really a huge kudos to the entire TNC Indonesia team, because that's a lot of fish pictures to go through. And all of those data, having a lot of data is all great and all, but we need to validate it. So to do that, we compare the total weight of the catch from a fishing trip from the coders data set with a control data set. And the control data set that we use for this is fishing receipts. Why receipts? It's because typically in the fishing operation in the Indonesian fisheries, the fish traders or the middlemen front the fishing costs with the expectation that those fishers will sell their entire catch to the fish traders or the middlemen. So between August and December 2017, I went back home to Indonesia and did my data collection there. Talked to a lot of fishers and captains, trying to get them to share with me their fishing receipts, which involves a lot of talking. And not all receipts are recorded in a way that you expect them to, so not all of them are usable, unfortunately. But we persevere because we're able to compare the total weight from the receipts data with the total weight from the coders data. And we found that the coders data set actually recorded a little bit more fish than the receipts. And that is because some of the fish were used as bait or eaten on board, or some of them are sold to other buyers, even though technically they're not supposed to do that. So this really emphasizes the importance of an onboard data collection. And we also found that 5 species contributed to 50% of their total catch. So even though the species captures more than 100 different species of snappers and groupers, we can start to narrow our focus on the main target catch. And the vessel sizes are also disproportionately small, between 1 to 10 GT in this fishery. After filtering the GPS coordinates, depending on the depth and the speed, this is just the spread of the fishing ground, again, which is all throughout the Indonesian archipelago. Now, from that 3.5 plus million photographs of fish, that allows us to update the maximum length, because we're seeing fish that's larger than previously recorded just from the sheer amount of photographs that we received. And some of them are larger than those that are recorded in FishBase. And that allows us to update the maximum length and then also update everything else. And having this updated life history parameters is really important, because it allows us to create this length frequency distributions. Here's an example of a length frequency distribution for Lucanus malabaricus, where you have length on the x-axis and you have the frequency, or how many fish is caught at that length, on the y-axis. And you'll see that a lot of the fish is caught smaller than the length at maturity. The majority of the fish is caught smaller than the optimal fishing length. Here's another example from Pristipomoides multidens. Again, similarly, a lot of the fish is caught smaller than the length at maturity, with the majority caught smaller than the optimal fishing length. And although these are only examples from 2 species in this fishery, unfortunately, this trend is quite common throughout the fishery. And it is especially pronounced in the Java Sea. And so based on these length indicator, there is quite a high risk to overfishing. And using other fishery indicators based on the trade limits and the SPR, for these 3 snapper species, there's a higher risk to overfishing. And for this one grouper species, the Epinephelus areolatus, there's a low to medium risk of overfishing. And we're gonna revisit this grouper species later down the line in the presentation. So try to remember that name, Epinephelus areolatus. But for now, we're gonna focus on these 3 snappers here. So the reason why the trade limit poses such a high risk to overfishing is because these snappers grow to pretty large sizes. So in order to fulfill demand for plate-side fillets or whole fish that fits on your dinner plate, fishers are catching the smaller immature fish. So now moving on to our next assessment using a different fishery indicator, which is the catch per unit effort, or CPUE. So remember when I said the CPUE was proportional to the abundance? Well, imagine if in the lower abundance population, I decide to change my fishing gear and catch using a large net instead, suddenly I can be catching as much fish as somebody would in a higher abundance fishing ground. So CPUE is not always proportional to the abundance. So does this mean that CPUE is completely useless then as a fishery indicator? Not so fast, because we can standardize the CPUE and still use it. So the definition for catch and effort that we use for our CPUE calculation is that the catch represents the total weight of the target species in the fishing trip, and the effort represents the total fishing days. And we calculate the CPUE per species fishing gear complex. So for our study, we just focus on 5 different species fishing gear complexes, and it is shown here. So we calculate the CPUE for Lucanus malabaricus caught by drop lines, and we calculate a separate one for Lucanus malabaricus caught by long lines, and so on. So now that we have identified what species fishing gear complexes we're going to focus on, there are 3 steps to getting to the final standardized CPUE values. First, we need to identify the relevant fishing trips. And then second, we need to calculate the nominal CPUE, which is just the catch divided by the effort. And then we're going to take that nominal CPUE and standardize it. So the first step to identify the relevant fishing trips. This step is really important because we only want to calculate the CPUE from fishing trips that is specifically trying to catch the target species and not just accidentally catching it on the side. And we use the species association approach to identify these fishing trips. And that's just using the catch composition to determine whether or not that fishing trip is really trying to catch that target species. And to do that, we use a logistic regression where we predict capturing that target species, and we regress that along the presence and absence of all the other all of the other species in the catch. And so after we've identified the relevant fishing trips, we can calculate the nominal CPUE and then standardize it. And the standardization procedure is basically trying to remove the different factors that makes the catch not proportional to the abundance. And to do that, we use a generalized linear method, specifically the delta log normal approach. And in this approach, we're actually modeling two things. The first part of the model, we're trying to model the probability of a zero observation, or the probability that you go out on that fishing trip and you don't actually catch the target species. And the second part of the model is that if you have a positive fishing trip, what is the CPUE? And for the first part of the model, we use a binomial distribution with a logit link. And for the second part of the model, we use the log normal distribution. So for the standardized CPUE itself, we're just going to multiply the estimated probability of catch, or that first part of the model, with the estimated CPUE, which is the second part of the model. And we can do that for every year, and that allows us to plot the standardized CPUE and the nominal CPUE for each species fishing gear complex. And here, the standardized CPUE is in red, and the nominal CPUE is in black. And the gray area is the confidence interval. And I'd like to point out that all of these values have been normalized. So what that means is that all dots that is above the black line is larger than the average, and all dots that's lower than the black line is smaller than the average. And you're looking at this and you might be thinking, okay, so is this a good thing or is this a bad thing? And frankly, we don't know, because we don't have CPUE from when this fishery is still in a pristine condition. And without having that baseline to compare it against, we don't actually know if this standardized CPUE values we're looking at is denotes like a good sustainable fishery or not. So again, so is the CPUE just not very useful then? Not quite. So we're going to plot the CPUE on each fishing ground. And here the CPUE is represented by these black dots, where the larger the dot is, the larger the CPUE value. And these areas denote Indonesia's fishery management areas, which is coded by these numbers. And the color represents the SPR, where green means that the catches from that area has a high SPR or more than 40%, and everything else means that it has a low to moderate SPR or less than 40%. So we can do that for each species fishing gear complex. And one might expect that in an area with a high SPR, you would have a higher CPUE or a higher catch rate. And in areas with a lower SPR, you'll have a lower CPUE or lower catch rate. However, we'll start to see that there are certain areas where it has a very low SPR, but the CPUE is the highest in the country. And you'll see that in several other species fishing gear complexes too. So what does that tell us? It tells us two different things. First, it tells us that it's really important to use more than one fishery indicator when we do assessments, because each indicator is actually assessing a different characteristic of the fishery. So for a holistic view on how this fishery is doing, we need to use more than one fishery indicator. And this is echoed throughout the scientific literature. And second, it shows us the possibility of a CPUE hyperstability. And CPUE hyperstability just means that the CPUE level remains high, even though the overall abundance declines. And that can be explained through high density of fish aggregations, because in really high density aggregations, even though the overall abundance of the fish declines, you can still be catching a lot of fish and be having a high catch rate. So just to recap our findings on the assessment using different fishery indicators, we found that there's a high percentage of immatures that's targeted and caught in this fishery. for a holistic view about this fishery, we need to use multiple fishery indicators. And we also identified potential fish aggregations that can lead to boom and bust phenomenon. And this boom and bust phenomenon just means that catch rates remain high, again, because of that high density fish aggregation, and then suddenly there's nothing and the fishery just collapses. So knowing that this fishery catches a lot of immatures, I use generalized additive models, or GAMs, to determine factors that lead to high proportions of mature fish in the catch. And to do that, I use the binomial distribution and use a combination of fishing factors and environmental factors as the predictors. And as part of the environmental factors, I use the bathymetric position index, or BPI, and also the roughness. So the roughness just shows that certain fishing areas, well, is more rough than others. And the BPI means that that fishing coordinate, if it has a higher BPI, is on crest or higher elevations. And if it has a lower BPI value, it means that it's on valleys or troughs. So based on this model, we found that there are different factors that's positively correlated with more mature fish in the catch, and then negatively correlated with more mature fish in the catch. But I'd like to focus on these two species here, that if you catch more of Epinephrus areolatus, or the grouper, hey, it's our old grouper friend, or we're catching a lot of the Atrabuca brevis, or the croaker, you're going to have more mature fish in the catch. And we believe that this is due to the ontogenetic habitat shift, where the grouper spends most of its juvenile days in shallow seagrass and coral reef areas. And as it matures, it moves to the deeper parts of the water. And that's where they're finally targeted by this fishery. Similarly, the Atrabuca brevis, or the croaker, spends most of its juvenile days in more shallow estuaries. And as it grows more mature, it moves to the deeper parts of the water, and it overlaps with where this fishery operates. On the opposite side, you have these three different snapper species where their juvenile habitats just completely overlap with where this fishery operates. Now that we know the different factors that leads to different proportions of mature fish in the catch, I'd like to simulate the catches at each of these fishing coordinates throughout the grid throughout Indonesian waters. And from the catch simulations, we found that there are several juvenile hotspots in Indonesia, and we define these juvenile hotspots as areas where more than 75% of the simulated catches are immature. And you'll see that there are several hotspots here, but not all of them hold the same importance. And that's because if we overlay them with the fishing coordinates, we'll see that not all of the hotspots overlap completely with the fishing coordinates. So let's just focus on those that do overlap. And it's shown in this map right here. I'd like to point out that the red boxes in this map represents pre-existing marine protected area boundaries, or MPAs. And so from this research, we've identified different juvenile hotspots, and catching less immature fish is really important for this fishery, because that's one of the main drivers of why this fishery has a high risk to overexploitation. So one might think, all right, well, let's just close off all these juvenile hotspots and not allow anybody to fish there. Well, not so fast. We can't do that for two reasons. First of all, the bathymetry and habitat data that we use in this GAM model is actually not detailed enough, and we need more detailed data to be able to really pinpoint where these juvenile hotspots are. And second of all, the Java Sea and Makassar Strait area is one of the most economically lucrative fishery, and it employs a lot of fishers. So we really need to balance conservation priorities and also the social and economic priorities when we try to curb fishing effort in these juvenile hotspots. So what can we do about it? So here is what we know. We know that Indonesia has a target to implement 200,000 kilometers squared of marine protected areas by the end of 2020. We're at about 96% of achieving that goal right now. So from the study, we believe that it's really important to also include portions of these juvenile hotspot as that network of MPA expansion, or including protection of deep slope demersal fishery as part of the MPA portfolio. So to recap on our suggestions on how to improve the sustainability of the fishery, We believe that the expansion of the MPAs to prioritize deep slope demersal fishery is really important. We think that changing the market preference for plate-sized fish is also important to shift that target limit. And we definitely need to implement different effort controls on key areas, such as the Java Sea and Makassar Strait, especially because there is juvenile hotspots there, and there's also the possibility of fish aggregations like shown in the map over here. And overall, I think this dissertation has captured the characteristics of the fishery, which has remained elusive prior to the implementation of the CODERS program by our collaborators in Indonesia. And we have preliminary ideas on where to proceed from here on improving the sustainability of the fishery. But this does not mean that our work is done. There's still quite a long way to go in this fishery. For example, future research can focus on how to better integrate the different fishery indicators. Again, because they're assessing slightly different characteristics of the fishery, we need a way on how to bring all of the conclusions together and come up with a good management action from it. And we also need more research on how to balance both the conservation priorities and also the social and economic priorities. Because again, the fishers in this fishery is disproportionately small scale. So whatever effort control that we implement, it's going to highly affect the coastal communities that are already vulnerable, like they're a vulnerable part of society to begin with. So there's definitely still a long way to go in this fishery before we reach that sustainable fishery status. But for me, I'm glad to say my dissertation's done. Thank you very much. And with that, I would like to say my thank yous to everybody. Huge thank you to my advisor, Dr. Austin Humphries, and my entire committee, Dr. Gavino and Dr. Hiro. Thank you so much for answering my incessant emails. Thank you very much to the chair, Dr. Nancy Carricker, for being the chair of today's defense. And I would like to say thank you to the entire Humphries lab, past and present. I genuinely mean it when I feel very uplifted by each and every single one of you. It's really such a positive collaborative experience to be part of the Humphries lab. I'd like to say thank you to my sources of funding. Thank you so much to Poseidon, with a special shout out to Arthi, Ernesto, and Steve. Ernesto, Steve, thank you so much for your codes. Codes are life, so you guys basically gave me life. Thank you so much for the RG Codes grant from the Nature Conservancy. Thank you to the entire TNC and PNCI team in Indonesia. You guys are really, really awesome, and I wouldn't have been able to do this research without you guys. A special shout out to Dr. Yospet, who is holding the whale shark, and Dr. Peter Mouse, who is not holding the whale shark, for helping me conceptualize this research and giving me ideas. Thank you for the entire team who helped me with data collection, helping me with logistics. Without your help, I probably would have, I don't know, probably died. And thank you for everybody who I always ask questions, specifically Mbak Lara, Hilda, and Bliwawan. Thank you for all of the data clarifications and all of your help. Definitely, thank you to all of the fishers who participated during data collection time, and we ended up spending a lot of time together chatting. And then here's a family of fishers who are seeing us off as we left the island after staying there for 1 week. I thought it was very sweet. In retrospect, he's probably just happy to see us go finally. And thank you to the entire Indonesian student body at the University of Rhode Island. You guys are awesome. Thank you to all of my friends who have supported me through all of these years. Even if your photo is not here, I'm thinking of you. With a special shout out to the Bali crew who helped me create a dance video for the Dance Year PhD competition. That was wild. And last but not least, I would like to thank my entire family. You guys have supported me even when I don't believe in myself. Thank you to my grandmother who called me her little professor since I was like 12 years old. Not sure if that was completely mentally healthy, but here we are. So thank you very much. And last but not least, I'd like to thank my beloved partner. You dropped your life in Indonesia and moved here with me to support me in my PhD. So thank you so much. I really don't think I would have made it this far without your help and support. Thank you very much. And with that, I will take any questions.
Thank you, Elle, for a really fascinating and excellent presentation. Well done.
Oh, thank you very much.
I'm going to facilitate the questions to keep us on track. So if anybody would like to ask a question of Elle, please type it in the chat. I will read out the question and then Elle, you can respond. Does that sound okay?
Yep, sounds good.
Great. Elaine will come up with a question after she's done crying, it appears. Questions, people. Elaine's quite proud of you, Elle, it seems.
Oh, thank you, Elaine.
Okay, here's a question from Oleg Kazakov. What is an example effort a regular consumer can make to better sustainability of fish production?
So I think as consumers, the best thing we can do is to not, of course, buy or consume these immature fish. But realistically speaking, it's very hard right now to even do that because we don't know the specific species, and different species mature at different lengths. And usually all of these snappers are just clumped into a general group, red snapper or white snapper. So frankly speaking, right now it's really hard to try to like make good consumer choices. But once you have better, I guess, species identification and markets, and when they're selling fish, that's when we actually can, I guess, use our money to vote or use our money to make good consumer choices.
Okay, Brian Cockrell asks, oh, sorry. As the questions fly up, the others drop to the bottom. What, would you expect the same conditions in the Philippines?
To be honest, I'm not quite sure what the fishery situation in the Philippines are. I know a little bit about the tuna fishery in the Philippines, which for tuna fishery, it's quite similar to the Indonesian tuna fishery, but I can't say how it is for the snapper grouper fishery, unfortunately. In terms of fishery management, it's quite similar between Indonesia and the Philippines, so I'm not going to be completely surprised if it's also overexploited there. But yeah, unfortunately, I can't say too much about the Philippines.
Okay, from Catherine Alves, do you have ideas about how to further include Indonesian fishers in the data collection and management process for this fishery?
So I'm going to answer that question, I'm going to steal an idea from what we have been doing for the tuna fishery in Indonesia, which is the formation of data management committees, where you include local government officials, like fishery officials, different fishers, fishing industry, and also NGO partners, and meet every like once half a year or at a predetermined time frame to come together and discuss the issues regarding the fishery. So that could be one step to do in the snapper grouper fishery. I know that our collaborators in Indonesia is doing also a lot of collaborative work with the fishing industry and fishers, because now the fishery is in the fishery improvement progress of the MSC certification. So there's also a lot of involvement from the fishers in that way.
Oma Kresning asks, I saw you have quite a bit of data, but you use annual data in the analysis. Do you think using smaller timescales would be able to present more information from the model?
Great question. Yes and no. And partly it's because there's actually different, like, I guess, cyclical events that happen throughout the year. For example, depending on the iklim, depending on like the different seasonality, there you go. Depending on whether it's like the westerly wind or the easterly wind, this fishing practices changes and the catch changes. So yeah, using smaller time scale would maybe be able to show those different pattern cycles, but we don't know enough about it to be able to see it in great detail. So that's definitely an avenue I think that would be interesting to look towards. But yeah, and it's also better, I think, to aggregate everything into an annual data set, because as this data collection system was just starting, we keep on adding new locations at different times of the year. And it was just, I think it makes a cleaner data to just clump everything together as an annual data set. Hopefully that answers your question.
Lynn would like to know, do you have any sense of the status of the multiple species of grouper you were not able to focus on?
Yeah, so in terms of grouper, the grouper tend to be in a better condition than the snappers. I think it's just by virtue of the fact that the groupers mature at a smaller size than the snappers, and then you have that ontogenetic habitat shift where the younger groupers don't overlap in the where the fishery operates here in Indonesia. So in general, the groupers are doing much better than the snappers in this fishery. However, because this assessment is only taking into account the data that we get from this fishery, we don't know how much of these groupers are being exploited, for example, from the coral reef fishery. So just because they look like they're in a good condition from our data set, they're probably also hammered because of a different fishery that targets them in those shallower areas.
Okay, we have 2 more questions, and then I'm going to call an end to the question session. So there are other people that are chiming in now, but maybe you can get back to them later, Elle. So you mentioned that it's difficult to impose an outright ban on fishing in areas with juvenile fish because many people's livelihoods depend on fishing these populations. What would a dialogue with Indonesian policymakers look like to find an environmentally and economically sustainable solution?
It will look very messy. It's going to be very challenging, if I may be so frank. And part of the reason why it's going to be very challenging is because we're seeing those really high catch rates at areas where are also juvenile hotspots. So imagine you're going in, telling a group of fishers who is catching so much fish, and you're telling them, all right, actually this fishery is not doing really well, and we're going to reduce fishing effort. You might just look a bit crazy at that point. You're like, no, we're catching so much fish. Why are you doing this to us? So I think this is where it's going to be really complicated. And I think we need to, if we are able to narrow the focus on where those juvenile hotspots are and kind of find a compromise between allowing them to still catch fish and protect that smaller area of juvenile hotspots, I think it'll be a lot less contentious that way. So yes. Short answer, messy. Long answer, with cautious optimism, we can do this.
That could be a dissertation in and of itself, correct?
Yes.
Okay. Final question comes from your lab mate, and Elle, I encourage you to look at the chat later perhaps and get back with any of the other people. Final question from your lab mate, Elaine. Is there a species consumption preference for those that came up negative in your GAM?
Negative. No, they're all part of like the really main species that's traded in this fishery. Some of them are actually sold together under the same common name. So yeah, they're pretty up there in terms of the preference.
Okay, great. Thank you so much, Elle, for a wonderful presentation. Thanks to everyone who showed up today. I cannot believe I tallied 63 at our maximum number today, which is just remarkable given that this was a virtual presentation. So thanks everybody for your attendance and your great questions. And we're going to close the session now to everybody except the committee. Thanks everyone and have a great day.
Thank you so much, everybody.